Okay, let's pick up where we left off in the last video and talk about sensitivity analysis for Bayes' decision rule. Um, so we kind of use Bayes' decision rule to compute the expected value for each of our alternatives, and the better expected value came from building the computers instead of selling the rights. But we might be a little bit curious on how does this expected value depend on the values of the prior probabilities? Okay, and the way to analyze that is to essentially let the prior probability be a variable, and then look at how this expected value changes with that variable. And then we can kind of compare if we got two decision criteria as we change the probability of one of the states of nature, how does the expected values for each of these change? And is one always better than the other, or is there some crossover point where one decision becomes better than the other? Okay, so one thing to note is that the probability of 60% for being in the cell 10K state and the probability of 40% for being in the cell 100K state, those two probabilities, if you only have two alternatives, should always add up to 1 or 100%. Okay, and so what we're going to do here to do sensitivity analysis for Bayes' rule, let's let P equal the probability of cell 10K computers. Okay, and that tells us that then 1 minus P is going to be the probability of selling 100,000 computers. Okay, and now what we're going to do is we're going to compute the expected values, but we're going to replace the prior probabilities with P and 1 minus P, and then we'll get essentially a function instead of a number, but a function that depends on the prior probability. Okay, so let's look at build. So in this case, we're going to do the expected value is going to be of the cell 10,000 is P, and we're going to multiply that by the value. If we only sell 10,000, we get a value of 0 plus 1 minus P times the value if we sell 100,000, or the payoff if we sell 100,000, and that's 54 million. Okay, 0 times P is 0, and so this ends up being 1 minus P times 54, or 54 minus 54P. Okay, and that's the expected value if we choose the build alternative. If we choose the sell alternative, we still have a probability of P of selling 10,000, and we get a value of 15 if we sell 10,000, and we get a probability of 1 minus P of selling 100,000, and we get a value of 15 if we sell 100,000. Now, if you do all the multiplication, we'll get 15P, and we'll get 15 minus 15P. The plus 15P and the minus 15P will cancel out, and we'll get exactly 15. So no matter what the probability is, no matter what the prior probability is, we're always going to get 15 million out of the sell option because that's the payoff for both of the alternatives. Okay, and you can think of an expected value as a weighted average, and anytime you do a weighted average of two identical numbers, no matter what the weights are, you're going to get that identical number. Okay, and so these are the two possible expected values. And now we want to look at, is there what we call a crossover point where these two expected values are equal to each other? Okay, so let's actually solve that. So our crossover is going to happen when 54 minus 54P equals 15. If we go ahead and do the algebra there and kind of move everything around, this will come out to happening when P equals 54 minus 15 is 39, but then divided by 54. And so that's about 72%. Okay, and so at a prior probability of 72%, chance, then the two payoffs are equal to each other, and this expected value is equal to this expected value, or so the build expected value drops down to 15. Let's actually graph this out as a function of P. And so on our vertical axis, we'll put expected value. On our horizontal axis, we'll put P. And really, we're going to kind of, the easiest thing is to think of 2 points. Here's where probability equals 0. Here's where probability equals 1. Now, our build has the function 54 minus 54p. When p equals 0, we get a payoff of 54. When p equals 1, we get a payoff of 0. Okay, and that's actually going to always be true. And you can more easily maybe see it over here, is that when p equals 1, we just get the 0, and this 1 minus p is equal to 0, so this gets turned off. When p equals 0, this gets turned off and this gets turned on. And so it will always be a straight line between those two payoffs in this case. And so we're going to have a value of 54 million up here and then go down towards 0. Okay, and so, oh, sorry, I was off the screen. So that's sort of the expected value as a function of P. It's 54 million when P is 0, but it's 0 when P is 1. The other criteria, or the other decision alternative, which is sell, has a constant value of 15 million. And so it's going to be just a horizontal line there. And then this point here where the two cross each other, that's going to be the crossover point. And so that happens at 0.72. So everywhere to the left of 0.72, we've got that this is the, maybe I'll write this. This is the build expected value. This is the sell expected value. And the expected value for build is higher than sell when probability P is between 0 and 0.72. And so if we think that the prior probability of selling 10,000 computers is anything less than 0.72, we should build. It'll have a better expected value. On the other hand, if the prior probability of selling 10,000 computers is between 0.72 and 1, then the sell expected value is higher than the build. And then, so in that case, we should sell. Okay, and so the nice thing about this sensitivity analysis is it gives us a crossover point. And similar to the max-min criteria, we now only have to decide, is that prior probability of only selling 10,000 computers more or less than 0.72? If we think it's more than 0.72, or about 3/4 chance that we'll not have a good rollout, then we should sell the rights. If we think that the probability of getting of a not good rollout is less than 0.72, which then we should build. Okay, and so simple, if P is less than or equal to 0.72, then we should build. If P is greater than or equal to 0.72, then we should sell. Okay, and if it's equal to 0.72, either would give us the same expected value, and then you could think about more about what's your risk tolerance as far as which would you prefer. Okay, and so that's kind of a discussion of sensitivity analysis. I will say when there are more than two states of nature, usually you only look at the probability of kind of two of those states of nature, and sort of you fix the third state of nature at a constant probability, and kind of look at the trade-offs between two of the states of nature. If you have more than two decision alternatives, you're essentially going to have multiple lines on this graph. So you might have a third decision alternative, which is maybe some sort of partnership where you exchange some of the profits for some of the risk. And so you partner with another company to build the computers. you take some of the risk, and so that might have a different line through here. And you'd kind of always look for which line is on top to determine which is the best alternative for that range of probabilities. Okay. So that's sensitivity analysis for Bayes' decision rule. It can kind of give you easier decision-making criteria of, do you think it's more or less than the crossover point?